Hi, welcome back to another lecture of solitons. This week we'll focus on conservation laws. So last time I introduced the basic idea of a conservation law. In general, a conservation law is something that tells us that a certain quantity does not depend on time. And we will follow a general strategy to derive a conservation law, which I introduced at the end of the previous lecture. So what we want to do is to look for two functions, rho and j, of the field U and its derivatives, such that they obey two conditions. So first of all, we would like the equation of motion for the field U, say the sine-Gordon equation or the KdV equation or any other wave equation that we might consider, should imply a partial differential equation, which is known as the continuity equation. So that's a statement that the partial derivative of rho with respect to time plus the partial derivative of j with respect to space x is equal to 0. So that's the first condition. And the second condition that we would like to hold is that the boundary conditions for the field U should imply that the limits of j as x goes to plus infinity and as x goes to minus infinity are equal and finite for all values of the time t. So why are these two conditions useful? Well, because then we can construct a quantity q, which we call the conserved charge, is given by the integral over space of rho. And we're going to show that the time derivative of q, the conserved charge, is 0. And that's why we call the charge or the quantity q conserved. Indeed, if we calculate the time derivative of this integral, we can bring in the time derivative inside the integral. That becomes a partial derivative of rho with respect to time. Then we can use the continuity equation to relate that to minus the partial derivative of j with respect to space, x. Now we have an integral over space of a total space derivative. And so we just get a boundary term, which is minus the difference of the limits of j as x goes to plus infinity and as x goes to minus infinity. But by the second assumption above, equation 4.4, that vanishes. So when conditions 1 and 2 holds, then q, the integral over x of rho that we call the charge density, is indeed time independent, and that's a conserved quantity. We then call rho the conserved charge density and j the conserved current density, or more briefly, just a conserved current. Today and next time, we will focus on finding conservation laws for relativistic wave equations, such as the sine-Gordon equation or the Klein-Gordon equation. But before we do that, let's first look at one example. I'll now go to full screen. The example that we'll study in section 4.2 is a conservation of energy for the sine-Gordon equation. The question that we would like to answer is the following. Is the total energy E, which is the integral over space of the energy density calligraphic E, conserved for the sine-Gordon equation where the energy density is the one that we wrote last week, namely a half ut squared plus a half ux squared plus 1 minus cosine of u. Notice that here the energy density plays the role of the conserved charge density, rho. So can we show that the partial derivative of the energy density with respect to time plus the partial derivative with respect to space of some quantity that we would like to find is equal to 0 if we use the sine-Gordon equation, which I remind you is utt minus uxx plus sine u equal to 0. And we also want to show that the limit of the current J, which appears in the continuity equation, are the same and are finite as x goes to plus or minus infinity. Okay, so let's calculate the partial derivative of the energy density with respect to time t. So I'm going to use a chain rule. So I get from 1/2 ut squared, I get ut utt. From 1/2 ux squared, I get ux uxt. And from 1 minus cosine of u, I get sine u times ut. So next I can collect together a factor of ut, which multiplies utt plus sine of u. And then I have plus ux uxt. So at this point, I can use the equation of motion, which is the sine-Gordon equation that I've written here. So utt plus sine of u is equal to uxx. So I get ut uxx plus ux uxt, which in turn I can write as a partial derivative with respect to x of ut ux. So we can now identify the quantity inside the partial derivative as minus the current J. And since the boundary conditions for the sine-Gordon field imply that require that partial derivatives of u with respect to t and x tend to 0 at infinity, in particular, they imply that the current J ut ux goes to 0 as x goes to plus or minus infinity. And the second condition that we need to obey, the condition that the current has the same finite limits at plus and minus infinity, also holds. And therefore, we can deduce that the total energy, which is the integral over space of the energy density calligraphic D, is conserved, which is indeed the statement of energy conservation. Next, we're going to try to generalize the previous argument to any relativistic wave equation, and in particular, we'll also use it to find some new or extra conservation laws. Relativistic wave equations in addition to the conservation of energy. I'll start by stating a few facts that we will use in the following. We'll take this also to define for us what a relativistic field equation or a relativistic field theory is. The first fact is that for any so-called relativistic field theory, in one space plus one time dimensions, where space is parameterized by x and time is parameterized by t. And examples of such relativistic field theories are the Klein-Gordon equation, the sine-Gordon equation, the phi to the fourth theory that we encountered in assignment, etc. So for any such relativistic field theory in one space and one time dimension, the energy, the total energy, is given by the following formula. So E is equal to the integral over space of the energy density, calligraphy E, which in turn is given by the general formula, a half ut squared plus a half ux squared plus a function v of u. For any relativistic field theory, the energy takes this form and is conserved. We'll derive this statement later today. When the equation of motion, or in brief EOM, which takes the general form UTT minus UXX equals minus V prime of U, is satisfied. As an exercise, please check this statement along the lines of the previous example. We'll rederive it later in a different way, but it's instructed to do this exercise. So please pause the video now and check that the energy is indeed conserved. You will have to assume some boundary conditions that you can derive from the general form of the energy in equation 4.7. So we see here that the theory is specified by this function v of u, which is called the scalar potential. For example, the scalar potential is 1 minus cosine of u for sine-Gordon. It's equal to 1/2 m squared u squared for Klein-Gordon, and it's equal to a quartic polynomial, say lambda over 2 u squared minus a squared, where lambda and a are parameters, all squared for the so-called phi to the fourth, or rather here we should call it u to the fourth theory, and so on. I should mention here that there is a very deep theorem due to M in Nether, so this is known as Nether's theorem, which shows that energy conservation, the statement that the total energy does not depend on time, follows from an invariance of the theory, or a symmetry of a theory. And the specific invariance or symmetry that implies the conservation of energy is the symmetry under time translations, where we shift time by a constant c. And similarly, invariance under space translations, where x is shifted by an independent constant I'll call c prime, implies the conservation of momentum. That's normally called P. We'll return to what momentum is. So you might have encountered this theorem, Netter's theorem, in previous courses. It's a really important result, but we won't assume it because it's of limited use for our purposes. But the point that I wanted to make here is that the conservation of energy and the conservation of momentum are very general. They follow from general invariance of relativistic theories under time translation and space translations. So in a sense, it's not a surprise that the energy and the momentum are conserved. But the question that we would like to answer is whether there can be more conservation laws. In addition to the conservation of energy and momentum for a relativistic field theory. And what we'll do today, and we'll finish in the next lecture, is we'll develop an argument that will allow us to answer this question constructively, meaning that we'll be able to construct extra conserved quantities or conserved charges if they exist, and we'll study under which condition these extra conservation laws hold. Before we answer this question constructively, we'll need to introduce some notation that will be very useful for bookkeeping. So that will be our first step in this analysis of conservation laws for a relativistic wave equation. So what we'll do is we'll switch from time and space coordinates to so-called light cone coordinates. Which are so dubbed because the axes, if we use this new light cone coordinates, are parallel to light rays. So what are these light cone coordinates? Well, we'll call them x plus minus, and they're defined as a half t plus or minus x. Where the sign on the left-hand side is correlated with the sign on the right-hand side. We can also invert this definition of the light cone coordinate to write the old time and space coordinates in terms of x plus and x minus. In particular, time t is x plus plus x minus, and the space coordinate x is x plus minus x minus. So then let's calculate the partial derivative with respect to the light cone coordinates, x plus and x minus. I will denote this as partial with the subscript plus minus. And we can compute those partial derivatives by using the chain rule. So these are given by partial derivative with respect to t times partial of t with respect to x plus minus plus partial derivative with respect to x times partial derivative of x with respect to x plus minus. Again, this is just the chain rule. So next we use the expressions above that relate t and x to x plus and x minus. So in particular, the partial derivative of t with respect to x plus or x minus is equal to 1. So the first term is simply partial derivative with respect to t, whereas the partial derivative of x with respect to x plus or x minus is either 1 or minus 1. So you will get the plus minus sign partial derivative with respect to x, which we also normally denote as partial t plus or minus partial x. Again, this is just notation. And therefore, from this, we can immediately conclude that a partial derivative with respect to x plus times partial derivative with respect to x minus is the same as dt plus dx is dt minus dx. So this is partial derivative with respect to time squared, so second derivative, minus second derivative with respect to space. And this is precisely the combination of derivatives which appears in a relativistic field equation or equation of motion. And so in particular, the equation of motion can be written more simply as u plus minus equal minus d prime of u, where here the notation is the usual notation that the subscript denotes a partial derivative. So the f plus or minus is a partial derivative of f with respect to x plus minus, or equivalent partial plus minus of f. In particular, if the scalar potential is a constant, then the equation of motion, which was originally utt minus uxx equal to 0, becomes u plus minus equal to 0. And that's precisely what D'Alembert used to find his general solution of the wave equation. But now we're interested in situations in which we have a non-trivial scalar potential v of u. Next, we'll define a useful quantity that we'll make use of repeatedly in the following, which is called the Lorentz spin. And we will be interested in the Lorentz spin of a monomial built out of light cone derivatives of functions of u. We define it as follows. The Lorentz spin is equal to the number of x plus derivatives minus the number of x minus derivatives appearing in the monomial. So for example, possible monomial could be u plus cube times q minus u plus plus minus, and this will have Lorentz spin, or just in brief spin, equal to 3 from u plus cube, minus 1 from u minus, which contains x minus derivative, plus 2 minus 1 from u plus plus minus, which has 2 plus derivatives and 1 minus derivatives. So in total, if my math is correct, this object has Lorentz spin 3. So why is the Lorentz spin useful? Well, because the laws of special relativity imply that objects of different spin transform differently under the so-called Lorentz group. Of symmetries of relativistic field equations. And as a result of this, objects of different spin don't talk to each other. And similarly, objects of different spins shouldn't be added to one another. Note, and this is a related comment, that we could use the equation of motion to relate u plus minus to minus v prime of u. And this does not affect the spin. So u plus minus has spin 1 minus 1, which is equal to 0, and v prime of u also has spin 0 because there are no night cone derivatives appearing. But the important point for us is that we will be able to focus on objects of definite spin. So we'll use the Lorentz spin as an organizing principle. We'll discuss objects of definite spin with increasing value from 0 upwards. I should say, for those of you who are interested, that I wrote some handwritten notes on the Lorentz group and the Lorentz spin, which are available on Duo, where you can find a bit more details on what the Lorentz group is and how the Lorentz spin is related to this group of symmetries of relativistic field equations. Those should be treated as extra material that you're welcome to read, but you won't have to know necessarily for the exam. Good. So next, we would like to rephrase the conserved charge density and the conserved current density in a way that makes more manifest the relation to relativity and their Lorentz spin. So what we'll do is the following. Let's suppose that there exists a pair of density densities T and X of spins S plus 1 and S minus 1, which I write in the subscripts, but sometimes I'll just write T and X. Such that they obey the following equation, that the derivative with respect to x minus of t s plus 1 is equal to the derivative with respect to x plus of x s minus 1. Note that both sides have a spin s, either because we have s plus 1 minus 1 from the derivative, or s minus 1 plus 1 from the derivative. In terms of the original coordinates x and t, we can rewrite this expression using the relation between partial derivatives with respect to light cone coordinates and derivatives with respect to space and time coordinates that I wrote earlier. We can rewrite this equation 4.11 as partial derivative with respect to t of t minus x plus partial derivative with respect to x of minus t minus x equal to 0. So we can identify t minus x as the conserved charge density rho, and minus t minus x as the associated current J. So equation 4.11 is nothing but the continuity equation or the local statement of the conservation law. And as long as the following condition on the limits of the current holds, so limit as x goes to plus infinity of t plus x minus the limit as x goes to minus infinity of t minus x is equal to 0 for all times, it then follows by the general argument of conservation laws that Q, the charge defined by the integral over space from minus to plus infinity of t minus x, the charge density, is a conserved charge. And it turns out that this conserved charge has a spin s. So we'll call it Qs. So brief comment here, you might be confused by the fact that in the integrand, I'm adding two quantities to densities of different spin, whereas I just said earlier that we should never add the objects of different spin. But the point here is that we're doing an integral over x, which also doesn't have a definite spin, but everything conspires in such a way that the conserved charge Q has a definite spin. That can be proven, but we won't do it here. So our aim will be to construct pairs of densities T and S with spins different by 2, which satisfy equation 4.11, which is essentially the continuity equation, equation 4.12, the condition on the limits, and that will allow us to construct a quantity 4.13, a conserved charge. So that's what we'll do next for the rest of the lecture, and also in the next lecture. To make our life easier, we'll make a simplifying assumption. Namely, we'll only consider so-called polynomially conserved densities. Namely, we'll assume that T is a polynomial in x plus derivatives of u. So we don't consider u appearing with an x minus derivative or u appearing without a derivative at all. So in particular, Ts plus 1 will involve exactly s plus 1 x plus derivatives. As we'll see, this will be enough to construct new conserved quantities. And also, we will mostly disregard total x plus derivatives in T. I will explain what I mean by mostly in a second. More precisely, we'll consider a pair of densities T and X to be equivalent to T comma T prime comma X prime, which differ from T and X by respectively adding a total x plus derivative of a function of spin S and the total x minus derivative of the same function of spin S. And now I explain what I mean by mostly. We'll disregard total x plus derivatives in T so long as the following condition on the limit holds, which is limit as x going to plus infinity of us minus the limit as x goes to minus infinity of us is equal to 0 for all times. Why are we entitled to disregard total derivatives in t and x so long as this limiting condition holds? Well, the reason is because the shifts in equation 4.13 cancel out in the continuity equation. And if you calculate the charge q prime s using the new or primed densities, let's say integral over x of t prime minus x prime, this is equal to integral over x of t minus x, which gives qs, plus a correction term, which is related to the shift, integral over x from minus to plus infinity of d plus us minus d minus us. But this difference of light cone derivatives is nothing but twice the derivative with respect to x. So this is qs plus 2 integral with respect to x, partial derivative with respect to x of us the integral now is an integral of a total derivative, so that's a boundary term. It gives us 2 times us at plus infinity minus 2 times us at minus infinity, but by equation 4.15, the condition that the two limits are the same, the correction term, the second integral vanishes, and so we find that the conserved charge defined using the new primed densities is the same as the original conserved charge. So in practice, we will disregard total x plus derivatives in t, so long as the quantity that we're taking a total derivative of has the same limits and finite limits at plus and minus infinity, because that has no bearing whatsoever on the conserved charge. Okay, so now let's start our constructive argument. We will proceed spin by spin. And unsurprisingly, we'll start from spin 0. In that case, the density T, which has a spin s plus 1, now has a spin 1 because s is 0. And we assume that the density is polynomially conserved, so it's a polynomial in x plus derivatives of u only. And here it's this polynomial can only contain one derivative, so up to a multiplicative constant, the only option is u plus. And we don't care about the multiplicative constant because that will only rescale the conserved charge. Now it's easy to see that this solves the continuity equation 4.11 with the associated current density x minus 1 being nothing but u minus. The reason is that if you compute the partial derivative of u plus or t1 with respect to u minus, we get u minus plus, which is the same as u plus minus, since we assume that the functions are sufficiently differentiable that the partial derivatives commute, but this is nothing but partial derivative with respect to x plus of u minus. So this is t1 and this is x minus 1. So then what is the charge q, which we expect to have spin 0? Well, that's the integral over x of t minus x, which is u plus minus u minus. But again, by relating light cone derivatives to space and time derivatives, this is by the same argument as above, twice the integral over x of the x derivative of u. So this gives us a boundary term 2 times the value of u at plus infinity minus the value of u at minus infinity. And this is nothing but the topological charge. Up to normalization. Note here that T1 is indeed the total derivative of u. However, you could have different limits at plus and minus infinity. In which case, the limiting condition 4.15, here it is, would not be satisfied by capital U equal to minus small u. And when that is the case, the topological charge will be non-trivial, meaning that it's not automatically equal to 0. So to be totally clear, notice that the boundary conditions, which follow from the general form of the energy, are that ut and ux go to 0 at special infinity, but also the scalar potential and its first derivative must go to 0 at special infinity. And this, if the scalar potential has sufficient structure, could allow that the limit of u as x goes to plus infinity is different from the limit of u as x goes to minus infinity. Essentially, if the scalar potential has different zeros, which are also stationary points, then this situation might happen. And in this case, the topological charge will be non-trivial. To conclude today's lecture, let's look at the next value of the spin, which is spin 1. So we'll look for a density T of spin 2, and therefore that density can contain u plus plus or u plus squared. So I mean by this that T2 will be a linear combination of u plus plus and u plus squared. But notice that u plus plus is a total x plus derivative of u plus. And since the boundary condition imply that require that first derivatives of u vanish, so in particular u plus will vanish at special infinity, we will be able to disregard this term because it will have no effect on the conserved charge. And therefore, we can take T2 to be proportional to u plus squared without loss of generality, and in particular up to normalization, we can take T2 to be equal to u plus squared. So now let's calculate the partial derivative of T2 with respect to x minus, so that's partial minus u plus squared. This is 2u plus u minus plus. And next we use the equation of motion, which is u plus minus is equal to minus v prime of u. So this is minus 2u plus v prime of u, which we can also write as minus 2 partial derivative of the scalar potential with respect to x plus. This is what we would like to identify with partial derivative of x naught with respect to x plus. So if we compare, we see that the x naught is equal to minus 2, the scalar potential. And therefore, we conclude that we have the following conserved charge of spin 1 integral over x of T2 minus x naught, which is integral over x of u plus squared plus 2, the scalar potential. This is equation 4.16. And we'll stop here for today. What we'll do next time is to understand how this conserved charge of spin 1 is related to energy and momentum. If you have any questions about this lecture, please use the discussion board or come to online office hour on Thursday. Otherwise, I'll post the next video in the coming days. Bye.